Our final project is on Raman spectroscopy. I'm Aaron Bashuk.
This is Luke Wells.
And I'm Yusuf Kabbalah.
So the introduction. So what is Raman spectroscopy? So spectroscopy is the usage of the electromagnetic spectrum of the light scattered off a sample to obtain information about what the sample's molecular and atomic structure is. Specifically, what Raman spectroscopy is the inelastic collision of electromagnetic waves with a molecule. And what makes it significant is that the Raman spectrum of a specific molecule is unique to that molecule. As you can see in the figure on the right, this is the Raman spectrum of different molecules, and they are all unique. So it's used in chemistry, physics, and biology to identify and study different molecules. This is a diagram of our spectrometer and how it works. So the incident light comes in, hits off a mirror, hits a grating, and that makes the light take different paths. And then it hits another mirror and goes into our CCD detector, which will tell you what wavelength you're seeing.
So here's a basic theory for spectroscopy. Okay, when a light of frequency f0 strikes the molecule of vibrational frequency f1, it creates an induced electric dipole. The first term is the Rayleigh scattering. The second term is the Stokes and anti-Stokes. We'll talk about those in a little bit. What actually happens is that the incident light transfers, or the molecule takes energy from the photon, which causes a change in energy. This can be modeled using quantum mechanics. And we're actually going to measure that using the Raman-shift, which has units of inverse length. And for the Stokes, the energy is transferred to the molecule. And for anti-Stokes, energy is taken away. For Rayleigh scattering, there's no change in the energy. Okay, so on to the experiment. First, we had to calibrate the spectrometer using a mercury lamp with known spectra from the literature shown here, which we will compare. When we calibrated it, we got a wavelength of 543 plus or minus 0.2 nanometers. The experiment, or the actual wavelength, is 546.07 nanometers with a percent difference of 0.04%. For the other two to the left of that, 404 and 435 nanometers, we calibrated it and we got a wavelength for the one on the right of 435.9 and percent change of 0.01, which is quite small. For the one on the left, we got a wavelength of 404.7 plus or minus 2, the percent change of 0.009. So both quite small. When we increase the wavelength of the laser striking on the spectrometer, or the intensity, it increases the amplitude of our peak.
This is our setup for the next part of the experiment, which is finding the Stokes scattering of two different molecules, which are polystyrene and polypropylene. So the first part of this is our laser, which is a 635 nanometer laser, which is red light. And then we shoot that into a mirror, which reflects to another mirror. And that goes into a focusing lens, which had a focal length of 35 millimeters. And that directed it straight onto our sample. And from there, most of the light went through, but the scattered light is random and goes in all directions, and we have to collimate the scattered light. So we want to use as small of a focal length as possible to capture the most data. So we used a 25.4 millimeter one. And then at 6, we have the notch filter, which gets rid of a lot of the red light to make our data less saturated. So our notch filter at number 6 lets through wavelengths from 527 nanometers to 797 nanometers, but filters out specifically 623 through 647 nanometers. So that filters out most of the Rayleigh scattered light that has the same wavelength as our 635 nanometer laser. And then 7, we have the actual spectrometer itself, and it actually shows the path it takes in it, which we showed earlier in a diagram. And then 8 is our CCD camera.
Next, we'll discuss the results that we actually got. So first is polystyrene. And this is an example of what polystyrene Raman spectrum looks like that you can find in the literature. And we found corresponding peaks to the ones here labeled 1, 2, 3, and 4. This first peak we have labeled 1. Our actual value that we got was 683.6 nanometers. That corresponds to a Raman shift of 1,119 inverse centimeters. And if you'll notice in the accepted spectrum, that's 1001. So ours is a little bit larger, and you'll see that is a bit of a trend. So in the second peak, we got a Raman shift of 1146. The third peak is a Raman shift of 1267, and the fourth peak is a Raman shift of 1670 inverse centimeters, which corresponds respectively to 1031, 1155, and 1602. So ours were larger in all of them, and it turns out they were all by about the same amount. And we'll discuss this further later. For the polypropylene results, so here you can see an example of what the polypropylene spectrum looks like in the literature, and we were able to find corresponding peaks to the ones labeled here 1 through 6. So this whole range could not fit in one view of our spectrometer, so here is the range from about 685 to 760 nanometers in wavelength. Our first one that we measured right here is about 690.3 nanometers, which corresponds to a Raman shift of 1262. And the second one has a Raman shift of 1417 inverse centimeters, and this third one is a Raman shift of 1539 inverse centimeters. And if we go back to the one from the literature, these are similar to the ones found here. Next, you can see this collection of peaks far from the exciting wavelength of the laser. And we have peak number 4. The peak we have labeled number 4 has a wavelength that we measured to be 778 nanometers. 5 is 780, and 6 is 784. These will give us Raman shifts of 2893, 2928, and 2991 inverse centimeters respectively. From the literature, these corresponding wavelengths are 2812, 2874, and 2941 inverse centimeters. But interestingly, all 6 of these are off by right about 5 nanometers. So we'll talk about this in our conclusion section. But importantly, the shape and the structure of them match very closely to what we can find in the literature. And you can see that right here. So 1, 2, and 3 match 1, 2, and 3, the shape and structure. They're just shifted by about 5 nanometers. So the sources of error that we believe this is coming from is the incident light not being collimated at the location of the grating, or at least not perfectly perpendicular. This is important because the diffraction grating separates the light, but the light needs to be coming in perpendicularly to the spectrometer in order for it to give an accurate reading. So we calibrated the spectrometer based on the location of the hydrogen lamp, but if the angle that the collimated light from our measurements are coming in from us is slightly different, then it's going to give a slightly different wavelength reading. Also, sources of error that we came into were we needed a long exposure time in order to actually read the peaks in the Raman spectrum. So when we are integrating over 60 seconds of exposure time, it allows lots of background light to enter into the spectrum. So here is an example of the location of the light changing what the perceived wavelength is. So you can see our calibration lamp, we're moving it in a circle from one side to the next, and as it's moving, it's changing what the reading of the wavelength is giving on the screen.
So in conclusion, our main takeaways are that the structure and shape of the spectra for polystyrene and polypropylene looked very similar to the respective spectra from the literature, as we saw earlier. And the main source of error was due to it was coming in at an angle when you want the incident wavelength to, or the incident angle to be 0. Otherwise, the wavelength of the reading will be shifted. And overall, we found around a 5 nanometer shift in our wavelengths, which caused our Raman shifts to be relatively massive. So where could we improve? A main thing would be to upload our data to a computer with the TrackQ Pro software, because the data files that were included or that TrackQ uses are not available to be used on a normal computer. You have to have their software to do it. And that would allow us to take the average of the images, which would help reduce the uncertainty and also help average out the random noise and error that we get from all the outside light due to the super long exposure time. And another place we can improve is expand our setup and make it much bigger. And to do that, we would use a telescope to concentrate the scattered light into the spectrometer, and that would make the intensity of our Stokes scattering much more intense. And by doing that, we won't need to use such a long exposure time. And here are our references. Thank you.